Bismillahirrahmanirrahim. Assalamu alaikum dear students, and welcome to the 31st lecture of Discrete Structures CSC 102. In the previous lecture we were discussing graphs. In graphs we have discussed Euler circuits, Hamiltonian circuits, and how to construct an Euler circuit and Hamiltonian circuits. We have discussed also a traveling salesperson problem. So such type of problems we can solve using these topics, Hamiltonian and Euler circuits. Today we shall continue some topics of continue discussing some topics of graphs, and we shall also start trees, which is the next topic in the theory of graphs. In today's lecture we shall discuss what are the relationship between matrices and graphs. Matrices you have I hope you have already studied in your FSC or FA classes 11-12. What is the matrices and directed graphs, and how to construct matrices from undirected graphs, and how to construct matrices from connected components of graphs. And then we shall move to trees and some properties of we shall discuss some properties of trees and then rooted trees if we have time. If no, we shall discuss rooted trees or trees in the next lecture in the detail. So what are the matrices? First, I repeat here some definitions of matrices so that you can remind what is a matrix. Basically graphs, how to represent graphs in computers. In a computer we cannot introduce a graph directly and discuss properties and other relations of graphs in a computer. For that, to introduce a graph in a computer, we have to translate the graphs into matrices. So first of all, we have to know what is a matrix. You have studied the definition. I repeat it here. M cross n, read as M by n. Matrix A over a set S is a rectangular array of elements of S arranged into M rows and n columns, like this. The matrix is basically, it contains elements. This is basically a row. These are the rows in a matrix, and this is M by n matrix, means order of this matrix is M cross n. And here we have columns in matrices. So these are called the elements of the matrices. For example, if you have a matrix of 3 rows and 3 columns, for example, we can write it as for example 1 2 3 4 5 6 7 8 9. So this is a matrix whose order is, you can say 3 by 3, means it has 3 rows and 3 columns. You can write some other matrices which contain only 1 row, 1 2 3. This is basically a matrix of order 1 cross 3 because it has 1 row and 3 columns. Similarly, you can write matrices which have 3 rows and 1 column, for example like this 1 5 9. It has 3 rows, 1 2 3 and 1 column, this. So this matrix is basically a matrix whose order is M by n. It's basically a rectangular array of M rows and n columns. Usually it is called rectangular, but it could be a square matrix. If rows and columns are equal, then we say that this matrix is a square matrix. So the ith row of A is this. Ith row means it could be first, second, third, fourth, any row, and jth column of A is given by this. The entry Aij is the ith row and jth column of A, and is called ijth entry of A. A matrix M by n is said to have size M by n or M cross n, and any two matrices A and B are equal if and only if all the entries, or first of all we have to check whether the size of both matrices is same, that is they have same size M by n, for example 2 cross 3 and 2 cross 3. And then the corresponding entries, means first entry must be equal to first, second must be equal to second, third must be equal to third, and so on, all the entries must be identical for two matrices to be equal. And a matrix for which the number of rows and columns are equal is called a square matrix, in which rows and columns are equal, that is 3 cross 3. And if a square matrix of size n, the main diagonal of A consists of all entries a11, a22, ann. For example, this, if you have this matrix, this basically, these elements are, this is basically called diagonal elements or main diagonal elements of A. For example, we had discussed the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. What is the main diagonal here? This is the main diagonal of this matrix. This is the main diagonal. Another property of matrices is that symmetric and anti-symmetric or non-symmetric matrices we'll discuss in further slides. Now, what is the relationship between matrices and directed graphs? How to construct a matrix if we are given a directed graph? By definition, the formal definition of this is, let G be a directed graph with ordered vertices 1, 2, 3 up to so on. Ordered means you keep the order of vertices, that is first come v1, second v2, third v3. We cannot write v2, v1, v5, v3, v4. Order of vertices must be maintained. First we write v1, second we write v2, and this so on vn. The adjacency matrix of G is the n cross n matrix A, where the entries of A are aij over the set of known negative integers such that aij denotes the number of arrows from vi to vj, means I to j. I represents here row, j represents here column. So if you have one vertex vi and one vertex vj, the number of arrows from this vertex vi to this vertex vj, this will be the element of this matrix A. So this is how we can construct an adjacency matrix of any graph G. For example, if we are given here an example this is basically the graph G, whole graph in part A. This is first part, this is second part of this example. Two directed graphs are given here, and we have to find adjacency matrix for these two directed graphs. So how to construct? Basically the elements of A are basically the number of arrows from vi to vj. Vi is where from 1 to n and j is 1 to n. These corresponds to rows and these correspond to column. So first of all we have to decide what is n, means how many rows and columns will be there in the matrix, in the adjacency matrix. In the graph G here we have 1, 2, 3 vertices. So first of all we have to calculate how many vertices are there in that graph. There are 1, 2, 3 vertices in this graph. So we must have n is equal to 3, and I is from 1 to 3, means 1 to 3, and j is also 1 to 3, means there are 3 rows and 3 columns in that adjacency matrix which correspond this graph. In part A, we have the same graph here G. There are 3 vertices, so we will have adjacency matrix of 3 rows and 3 columns. How to construct this matrix? First you write here v1, v2, v3 in rows, and then v1, v2, v3 in columns, and then you write here a bracket. Then you calculate here what will be the first entry. First entry means how many arrows are there from V to V1? Here from V to V1 there is no arrow. There is no arrow, because here from V2 to V2 here we have one arrow, which is a loop. On V1 there is no loop, therefore the directed arrows from V1 to V1 are 0, so we write here 0. Now from V1 to V2, if we want to check from V1 to V2, here we have from V1 to V2, this corresponds this and this corresponds this. How many arrows are there from V1 to V2? From V1 to V2 there are no arrows. You can see here from V1 to V2 there is no arrow, so 0, we'll write here 0. The number of arrows from V1 to V2 is 0. Now again from V1 to V3, how many arrows are there from V1 to V3? So here from V1 to V3 there is no arrow, because there are two arrows which are from V3 to V1, that you can see the direction here. So from V1 to V3 there is no arrow, so we write here 0. Now come to the second row. From V, here we have V2, here we have V1. So we have to calculate arrows from V2 to V1. So how many arrows are there from V2 to V1? Here V2 to V1, here we don't have any arrow, so therefore we write here 0. Now from V2 to V2, here how many arrows are there from V2 to V2? So from V2 to V2 we have one arrow. You can see its direction here. So here you have to calculate the directed arrows. We have only one directed arrow from V2 to V2, so therefore we write it here 1. Now this entry from V2 to V3, how many arrows are there from V2 to V3? So here you can check by looking at the graph and see how many arrows are there from V2 to V3. So there is only one arrow, this one, which is from V2 to V3 because of its direction here, you can see. So there is only one arrow from V2 to V2 to V3, so we write here 1. Now coming to the third row, from V3 to V1, how many arrows are there? From V3, here we have V1. How many arrows are there? This arrow is from V3 to V1. This arrow is also from V3 to V1. So there are two arrows from V3 to V1. So we write here 2. Next, from V3 to V2. From V3 to V2, there is only one arrow, which is this one. So we write here 1. From V3 to V3, there is no loop on V3. Therefore, we write here 0. So this is how we can calculate adjacency matrix corresponding to this graph. Similarly, now we have to calculate adjacency matrix for this graph. How many, first of all, you have to check how many vertices are there in this graph. We have V1, V2, V3. There are 3 vertices in this graph. Therefore, the adjacency matrix have 3 rows and 3 columns. So we write here V1, V2, V3. Here V1, V2, V3. So these V's correspond to rows. These V's correspond to columns of that matrix. First of all, we check how many arrows are there from V1 to V1. So there is only one arrow from V1 to V1. So we write here 1. From V1 to V2, V1 to V2, we have one arrow. This one, we write here 1. From V1 to V3, there is no arrow. We write 0. Similarly, we can calculate this adjacency matrix, which correspond the given graph, and we can introduce it in computer, or for further analysis and operations we can use this adjacency matrix. So this is how we can calculate adjacency matrix for a given directed graph. Now, what is the reverse? how to obtain a directed graph from a matrix. First, in the previous slide we have learned how to calculate an adjacency matrix from a given directed graph. Now we do the reverse of this procedure. If we are given a matrix, how to construct a directed graph. So this is the given matrix. How many rows are there in this matrix? 1, 2, 3, 4. How many columns are there? 1, 2, 3, 4. So there must be 4 vertices in that graph. We say them v1, v2, v3, v4. Now we check, we plot v1 here, v2 here, v3 here, v4 here. Anywhere you can plot 4 points. We say it, this is v1, this is v2, this is v3, this is v4. Now we check the entries of this matrix. This is 0. It means there is no loop on v1, that is, there is no directed edge from v1 to v1. So it's 0, so it is sufficient here. Then from v1 to v2 there is one arrow. From v1 to v2 there is one arrow. We draw an arrow from v1 to v2 directing this. The direction must be specified here, because here from v1 to v2 we see 1. If you want to see from v2 to v1, then you have to investigate this v2 to v1, this. So from v1 to v3 there is one arrow. From v1 to v3 there is one arrow. From v1 to v4 there is no arrow. So we stop here at the first line. Now we consider the second row. From v2 to v1 there is one arrow. So we construct here another arrow, this one. From v2 to v2 there is one arrow, so it must be a loop. We construct a loop here. From v2 to v3 there is no arrow. From v2 to v4 there are 2 arrows. From v2 to v4 there are 2 arrows, so we draw 2 arrows from v2 to v4. So from now we come to the third row, v3 to v1 there is no arrow. From v3 to v2 there is no arrow. From v3 to v3 there is one arrow, so it must be a loop. So we constructed our loop here. From v3 to v4 there is one arrow. From v3 to v4 there is a one arrow. We draw this arrow. Now we come to the fourth row. From v4 to v1 there are 2 arrows. From v4 to v1 there are 2 arrows. We plot these arrows. From v4 to v1 there are, from v4 to v2 there is one arrow, so we construct a one arrow from this one here. From v4 to v3 there is no arrow. From v4 to v4 there is no arrow. So this is our directed graph which correspond this matrix. This is basically adjacency matrix. So this is basically the same as we have constructed here, except the direction we must have this. Okay, this is basically the corresponding directed graph. So this is how we can construct a directed graph from for a given adjacency matrix. Next is basically matrices and undirected graphs. What is the formal definition of this undirected graph? How to construct the adjacency matrix? Let G be an undirected graph, any given undirected graph, for example this one, with ordered vertices v1, v2, vn. Ordered vertices, that is, we have to keep the order of vertices. The adjacency matrix of G is the n cross n matrix A, where A is equal to Aij. Aij are the entries over the set of non and negative integers, such that Aij is equal to the number of edges connecting Vi and Vj. Now here there is no direction arrows, we have to just investigate how many arrows are there which connects a vertex vi to a vertex vj, from one vertex to another, some other vertex. So this is enough. We don't see here, we don't look at the direction of the edges. So for example, we are given an adjacency matrix for a graph G. No, we have to find an adjacency matrix for a graph G given below. This is the graph whole J graph, we call it G. Now first of all, how many vertices are there in this graph? v1, v2, v3, v4. So we have 4 vertices in this graph. So the adjacency matrix must have 4 rows and 4 columns. For example, we say first row v1, v2, v3 and v4, v1 first column, v2 second column, v3 third and v4. Now we have to see how many arrows are there from v1 to v1. v1 to v1, there is no loop here, so the first entry will be 0. From v1 to now how many edges are there which connects v1 and v2? v1 and v2 here, not from v1 to v2, because here we don't have directed arrows, we have just have edges. How many edges are there which connects v1 and v2? So there is only one edge which connects v1 and v2, so we write here 1. Similarly, how many edges are there which connects v1 and v3? v1 and v3, v1 and v3. There is no edge which connects directly v1 and v3, so we write here 0. How many edges are there which connects v1 and v4? There is only one edge, so we write here 1. Now how many edges are there which connects v2 to v1? We have already calculated it, it's 1. How many edges are there which connects v2 to v2? v2 to v2, there is a loop here, so there is one edge which connects v2 with v2. So how many edges are there now which connects v2 to v3? There are 2 edges here, v2 to v3, which connects v2 and v3. So we write here 2, v2 to v4 1, v3 to v1 no, v3 to v2 2, v3 to v3 0, because there is no loop here. v3 to v4 no, v4 to v1 1, v4 to v2 1, v4 to v3 0, and v4 to v4 1, because there is a loop here. So this is basically the corresponding adjacency matrix of this undirected graph. So what we have done on the previous slide, this is a graph and this is the corresponding adjacency matrix of this undirected graph. This matrix is symmetric. How? You have studied in FSC or FA in 11th class, you can first year, that if we take the transpose of a matrix, that is if we change the rows into columns and columns into rows, that is if we take the transpose of this matrix, what is the first row? This is the first row, we write it in column 0 1 0 1. We take the second row here, we write it in column 1 1 2 1. This is the third row 0 2 0 0, and the last row is 1 1 0 1. Now you see whether there is a difference between these two matrices. We get the same matrix 0 1 0 1 0 1 0 1 1 1 2 1 1 1 2 1 0 2 0 0 0 2 0 0 1 1 0 1. So such type of matrices are basically called symmetric matrices if the transpose of a matrix comes again the same matrix. In constructing the adjacency matrix of undirected graphs, we obtain always a symmetric matrix, whereas in calculating adjacency matrix of the directed graphs, we obtain unsymmetric matrix or non-symmetric matrix. Non-symmetric matrix, this is basically non-symmetric matrix or anti-symmetric matrix, you can say that. You can say non-symmetric matrix, whereas this matrix which is the adjacency matrix of a undirected graph, this is basically a symmetric matrix. Next is matrices and connected components. Consider a graph G as shown below, that consists of several components, connected components. So this whole is basically the graph G, and these are all connected components. This is H1, for example, this is H2, and this is H3. H1 is connected component, H2 is connected component, H3 is connected component of G. We have already discussed in the previous lecture what are the connected components of a graph. And now we have to compute the adjacency matrix for the graph G, the whole graph G, this. So first of all, we have to calculate how many vertices are there in this graph. There are V1, V2, V3, V4, V5, V6, V7. So there are 7 vertices here in this graph in G. So the adjacency matrix, the matrix A, must have 7 rows and 7 columns. So it should be a 7 by 7 matrix. The size of this matrix should be 7 rows and 7 columns, like this. So we write also V1 here, V2 here, V3 here, V4, V5, V6, V7, V1, V2, V3, V4, V5, V6, V7. Now we write the first connected component H1, V1, V2, V3. We calculate how many arrows are there from V1 to V1. There is only one arrow, so we write here 1, just as we have calculated the adjacency matrix for directed and undirected graphs. We write all the entries here. Now basically V1, V2, V3, this correspond to first connected component. V4, V5, this correspond the second connected component, and V6, V7 correspond the third connected component of a graph. Here this is for second component and this is for third component. This is basically H1, this is H2, this is H3. Here we have H1, here we have H2, here we have H3. The matrix, we can divide the matrices into by these dotted lines. This. Here H1, the vertices of H1 cannot be connected by the vertices of H2 because H1 is a connected component, H2 is another separate connected component. So when we have these entries, we can directly write them 0 because this is a connected component of G, and only the vertices of one connected component are related, or they are connected through arrows. and one connected component cannot be, the vertices of one connected component cannot be connected to vertices of other connected component, so we directly write 0 here. So these lines basically represents the connected components. This first matrix, this matrix correspond to the adjacency matrix, correspond to the first connected component H1. This matrix corresponds to the connected component H2. This matrix corresponds to the connected component H3. All other entries will be 0, and basically they are all 0. Sometimes if we write them with a big 0 like this is also valid. 0 like this, 0 like this, 0 like this, 0 like this. We can write the adjacency matrix immediately like this. So because this corresponds to H1, this corresponds to H2, this corresponds to H3. So this is how we can calculate an adjacency matrix for a graph who has connected components. Next is the isomorphisms of graph. What is basically the isomorphism? What does it mean? Isomorphism is basically the word isomorphism comes from the Greek, means same form. It means same form. That is, we have to check whether two graphs are of the same form or not in this topic, isomorphism of graph. As we have discussed one example in which we have discussed that if we change the labeling of the graph, the appearance of graph will be different, but in actual the graphs are same. The edge endpoint function, as we have discussed in the first lecture of graph, that edge endpoint function functions of these two graphs 1 and 2 are same. So we can do it by change the labeling of the graph. But here, if suppose we consider this graph as a one graph and another graph, this one we call it a G dash graph, this we call it G. You can see that both these graphs have same form, but the position of vertices have been changed here. That basically these two graphs are different, because you can see here that the edge E1 has endpoints V1 and V2. Here edge E1 has endpoints V1 and V3. So here these two graphs are different, but we can define a function like this. Here observe that G dash is different graph from G. For instance, in G the endpoints of E1 are V1 and V2, whereas in G dash the endpoints of E1 are V1 and V3. Yet G dash is certainly very similar to G. G dash is very similar to G. In fact, if the vertices and edges of G dash are relabeled, if we relabel this, if we change the labeling of this graph G dash, it will become G. So if we define a function here between the vertices of G and G dash and edges of G and G dash, here we define here one function from vertices of G to G dash. We say that V1 remains V1, V2 is changed with V3, V3 is changed with V5, V4 is changed with V4, V5 is changed with V2. And similarly, edge corresponding to these this function vertices, we also define a function between the edges. E1 remains E1, E2 becomes E3, E3 becomes here E5, E4 becomes E2, E5 becomes E4. If we apply these transformations, these functions, these relabeling functions, you can say them, then the two graphs will become identical. And you can note that these relabeling functions, this and this one, are both 1 1 and on 2. That is, there is one-to-one correspondence between the elements of G and G dash, between the vertices and edges of G and G dash. So relabeling functions are 1 1 and on 2. We have studied in detail what are the 1-to-1 and on 2 functions when we have studied functions. So the two graphs that are same except for the labeling of their vertices. Two graphs that are same except for the labeling of their vertices and edges are called isomorphic. Isomorphic means they have same form. They are of same form. So two graphs are isomorphic if there is a one-to-one correspondence between the vertices of two graphs and edges of two graphs. So such type of graphs are called isomorphic, or we can say that there is an isomorphism between these two graphs. So now the proper formal definition of isomorphism of graph. Let G and G dash be graphs with vertex set V of G and V of G dash, and edge sets E of G and E of G dash respectively. G is isomorphic to G dash if and only if there exists one-to-one correspondence G between the vertices V of G to the vertices of G dash, and H between the edges of G and edges of G dash. For example, here you can say that this is a one-to-one correspondence G from vertices of G to vertices of G dash, and this is a one-to-one correspondence H from the edges of G to the edges of G dash. That preserves the edge endpoint function of G and G dash. That preserves the edge endpoint function of G and G dash. What does it mean? It means that if you have one vertex in the graph G, any vertex in graph GV, then it is an endpoint of E if and only if G of V is an endpoint of H of E. Means here you can say that here, if in the graphs, for example, here V1 is the endpoint of E1, then in the other graph V1 must be the endpoint of E1 also. So that is the edge endpoint function must be preserved, must be same in the isomorphism when you define the one-to-one correspondence between edges, vertices and edges of two graphs G and G dash. For example, here we are given two graphs, one is G, the other is G dash. Now we are going to find the one-to-one correspondence between these two graphs to show that these two graphs are isomorphic, that is, they are of the same form. What things we have to care in finding the isomorphism? There are, first of all, you have to check there must be same number of vertices of these two graphs, there must be same number of edges between these two graphs. Then we move further. Here we have V1, V2, V3, V4, V5. So there are 5 vertices. Here we have W1, W2, W3, W4, W5. We have 5 vertices. So we can define one-to-one correspondence between the vertices of these graphs. And then check the edges. We have E1, E2, E3, E4, E5, E6, E7. We have 7 edges in this graph, and in this graph we have F1, F2, F3, F4, F5, F6, F7. So we have 7 edges in this graph also. So we can define there may exist one-to-one correspondence between edges of G and edges of G dash. Now what more things we have to care about here in finding one-to-one correspondence between these two graphs. So to solve this problem, you must find functions g from v of g to v of g dash and h from e of g to e of g dash, such that for all v belongs to v of g and e belongs to e of g, v is an endpoint of e if and only if g of v is an endpoint of h of e. So setting up such functions is partly a matter of trial and error. That is, you just hit and trial method, just guess, and partly a matter of deduction. That is, you use the logic also. For instance, since E2 and E3 are parallel edges, have the same endpoints, that is E2 here, E2 and E3 are parallel edges. So E2 and E3, these both edges must be related to F1 and F2, because F1 and F2 are also parallel edges. And then, for example, V1 has degree 1, 2, 3, 4, and where we find some vertex here which has also degree 4. W2 is the vertex which has 1, 2, 3, 4. So V1 must be related to, or must be transformed to W1. There must be. So we care about such type of issues here in these two graphs, that if V1 has degree 4, you cannot connect V1, or you must not connect V1 to W1 or W3, because V1 has degree 4, W1 has degree 3, W3 has degree 2. So you have to care about these things to construct or to find the one-to-one correspondence between vertices and edges of G and vertices of edges and edges of G dash. So there is one type of correspondence, one-to-one correspondence given here. You can find some other. There may exist many one-to-one correspondence between the vertices of G and vertices of G dash and edges of G and edges of G dash. So if we connect V1 to W2, V2 to W3, V3 to W1, V4 to W5, V5 to W4. So this gives you the one-to-one correspondence between the vertices of G and G dash, and similarly this H one-to-one correspondence between edges and edges of G and G dash. So we can define the one-to-one correspondence like this between the vertices and edges of these two graphs. If we are succeeded in finding a one-to-one correspondence, then we can say that these two graphs are isomorphic, that is, there. Next is an invariant property in the graph isomorphisms. A property P is called an invariant for graph isomorphism if and only if, given any two graphs G and G dash, if G has property P and G dash is isomorphic to G, then G dash has also property P. Now what is this property P? It could be anything: number of vertices, number of edges, degree of a particular vertex, or if this graph has a simple circuit or not, this graph is connected, or there are many properties you can check within a graph. We say it a property P. That property is invariant if invariant in two graphs, if there is an isomorphism between the two graphs G and G dash. For example, here in these two graphs we can check that there is a vertex in the graph G. There is a vertex in the graph G whose degree is 4. For example, V1 has degree 4. So only one vertex, there is only one vertex in graph G whose degree is 4. This it is a property of this graph. Now we have defined we have showed here that there is a one-to-one correspondence between these two graphs, that is these two graphs are isomorphic. So this property must be preserved, must be invariant in G dash also. What does it mean? It means that there must be only one vertex in G whose degree is 4. That is, there must exist some vertex, only one vertex in G dash whose degree is 4. You can find that vertex. Now what is that vertex here? W2 is that vertex whose degree is 4, so we can write here W2. So this property is preserved here. This property is invariant here in this graph. You can check some other properties. For example, there are two vertices V3 and V4 whose degree are 3. Degree of V3 is 3, degree of V4 is 3. So there are two vertices whose degree is 3. Here we must also have in this graph two vertices whose degree must be 3. So which are W1 degree has, the degree of W1 is 3, the degree of W5 is also 3. So there are two vertices whose degree is 3. We can check other properties as well, for example, which are given here. The graph G has n vertices. The graph G dash must have also n vertices if there is a isomorphism between G and G dash. If graph G has a simple circuit of length k, then the graph G dash must have also a simple circuit of length k. If graph G has m edges, then graph G dash must also have m edges. If graph G has vertex of degree k, then G dash must have also a vertex of degree k. K could be 2, 3, 5, anything. If graph G is connected, then G dash must also be connected. If graph G has a circuit of length k, or if a graph G has an Hamiltonian circuit or Euler circuit, then G dash must also have Hamiltonian and Euler circuit. So this is what an invariant property, and in this theorem they have discussed properties. You can check the proof of this theorem in the book. So showing that two graphs are not isomorphic. Show that the following pairs of graphs are not isomorphic by finding an isomorphic invariant that they do not share. Means we are trying to find some property which is not common in both graphs, and we can conclude that these two graphs are not isomorphic. For example, in part A we are given two graphs G and G dash. G has 9 edges, we can immediately see, and G dash has only 8 edges. Therefore these two graphs are not isomorphic. In part B we have two graphs H and H dash. H has a vertex of degree 4. This vertex of H has degree 4, 1, 2, 3, 4. But whereas in the graph H dash we don't have any vertex whose degree is 4, because this vertex has degree 3, it has 3, it has 3, it has 3, it has 2. So there is no vertex in H dash whose degree is 4. Therefore we can immediately say that these two graphs are not isomorphic. These are also not isomorphic. For graphs it's I think enough. We stop here, and now we are going to start the trees. Trees, what is basically a tree? Tree is basically a graph is said to be circuit free if and only if it has no circuits. Circuit, that is, you know the definition of a circuit. Just remind the definition of circuit and then start the trees. A circuit is a basically a walk which starts from a vertex which ends at the same vertex, which can repeat vertices but which cannot repeat the edges. So this is the definition of circuit. And a graph is said to be circuit free if and only if it has no circuits. A graph is called tree if and only if it is circuit free and connected. So any graph which is circuit free and connected is called a tree. And a trivial tree is a graph that consists of a single vertex. That is, if you are given one vertex here, for example in this graph is basically a tree, but it is a trivial tree. So what is a tree? Basically a tree is a graph who is circuit free and connected. So here are examples of some trees. This is basically a tree. This is a graph. Yes. It's connected. Yes. It is circuit free. Yes. There is no circuit, that is, we cannot reach at the same vertex from starting. You can choose any vertex. This we cannot go through the graph and come back to the same vertex by using edges exactly once. That is, we cannot repeat the edge in a circuit. So therefore there is no circuit in this graph. It is circuit free and also connected. So it's a tree. It's a trivial tree because it has only one vertex. It's also a tree because it's circuit free, connected. Yes. It's also a tree because it's a circuit free and also connected. Now some of the examples of graphs which are not trees, because this circuit is not a tree because it has a circuit, because we can reach by starting from here, we can come back here. So it's a basically circuit here. So it's not circuit free. This graph is not circuit free, so it's not a tree. This is non-tree. Yeah, you can say that, not tree. This graph also have a circuit here. We can start from here and we can come back here. So it's also a circuit here. It's not circuit free, so this is not tree. This is also a circuit. This is not tree also. This is not tree. Why? This graph is not connected. This graph is not connected. So by the definition of a tree is a graph which is circuit free and connected. That is called a tree. So we can check these two properties in a graph and we can decide whether it's a tree or not. So the practical examples of trees where we can use trees in solving problems of daily life or such type of problems. An example of this is adjacency tree. You can find some other examples in the book of Discrete Mathematics by Rosen and Susena. Adjacency is basically during orientation week, a college administers an exam to all entering students to determine placement in the mathematics curriculum. The exam consists of two parts and placement recommendations are made as indicated by the tree shown in the figure. Read the tree from the left to right to decide what course should be recommended for a student who scored 9 on part 1 and 7 on part 2. Basically there are some students who take part in the entering exams to get an admission in college or to take some courses in particular semester in the university. You can say that there are if you are studying in a university in BS Computer Science, in a first semester you get in the first mid or in the second mid, you can say, or in first semester and second semester, you can say that you scored some marks, you obtained some marks, and on the basis of these marks in the first and second semester, you are going to choose subjects in the third semester. For example, in the score on part 1 in the first semester, if you scored greater than 10, and in the second semester you scored greater than 10, you can choose Math 120. Math 20 is one course, and if you choose in the first semester greater than 10 marks and in the second semester less than or equal to 10 marks, then you can choose Math 110. Math 110 is a course. Similarly, if some student has got 8, 9 or 10 marks in first semester, and in second semester they got greater than 6 marks, then they can opt Math 110. And in second semester, if they obtain less than or equal to 6 marks, then they can opt Math 100. These are all the courses. And if in the first semester some student got less than 8 marks, then he can only choose this course. So these are basically the grading, you can say that. Now we have to by seeing this tree from left to right, we have to decide what course should be recommended for a student who scored 9 on part 1 and 7 on part 2. So he got 9 marks, so he will come here, and in second part he obtain 7 marks, which is greater than 6, so he'll come here and he will opt this course. He can opt this course in the third semester or third session, you can say, whatever. So such type of applications we can solve by using trees. Now a very important result, I have summarized all the theorems in this which are given in the book of Cesena in one theorem. All these results are basically the separate theorems in the book. You can find the proof of these theorems. I'm not including the proof of these theorem here. The first theorem is basically any tree that has more than one vertex has at least one vertex of degree 1. So it's obvious. For example, if we have 2 vertex in that tree, v1 and v2, and it is connected, so it has at least one vertex of degree 1. So it has this vertex of degree 1, this vertex of degree 1, so it's possible. So this is our first theorem. The second theorem is for any positive integer n, n could be anything, 2, 3, 5, 9, 12, 25, anything. Any tree with n vertices has n minus 1 edges. For example, in this tree has 2 vertices and 1, that is, which is 2 minus 1 edges. So these are edges, these are vertices. So this is what they said in the second theorem, that is, if a tree has n vertices, its edges must be n minus 1, means vertices minus 1. The third theorem is for any positive integer n, if G is connected graph with n vertices and n minus 1 edges, then G is a tree. So this is basically more information about graphs, so that we can check whether this graph is a tree or not. If the graph G is connected and n vertices and n minus edges, this graph must be a tree. You can verify it. For example, this one is a simple, it has 4 vertices and 3 edges, 1, 2, 3 edges. It's a graph, it's connected, so it's a tree. It must be a tree. Similarly, this one, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It has 15 vertices. so it must have 14 edges. It's connected, so it's a tree. Edges 1 2 3 4 5 6 7 8 9 10 11 12 13 14, so it has 14 edges. So according to that theorem, it's a tree. So it's really a tree. We have discussed it earlier. So these are three important results which we can draw in the trees. Now let T be a tree. If T has only one or two vertices, then each is called a terminal vertex. For example, here, as we have supposed that this tree, it has one or two vertices, so both of these are basically terminal vertices. This is also terminal, this is also terminal, because it there is no edge further connected with V1, so it's a terminal, it's finishing. If T has at least three vertices, then a vertex of degree 1 in T is called a terminal vertex or a leaf, terminal vertex or leaf, and a vertex of degree greater than 1 in T is called a internal vertex or a branch vertex. For example, this is a tree. Basically it's a graph, it's connected, there is no circuit here in this graph, so it's a tree. Terminal vertices are those vertices whose degree is 1. This vertex has degree 1, this vertex has degree 1, this vertex has degree 1, degree 1, degree 1, degree 1. So all these vertices are terminal vertices because they have degree 1, and all those vertices whose degree is greater than 1, for example V6, V1, V3, are all vertices whose degree is, its degree is 2, 3, its degree is 3, its degree is 1, 2, 3, 4. So these vertices are internal vertices or branch vertices, and terminal vertices are called also leaves. So this is a terminology which we use in trees. Now an example is a graph G has 10 vertices and 12 edges. Is it a tree? By using the theorem, we have that a graph which has n vertices and n minus 1 edges, it will be a tree, and it should also be connected. No. The answer to this example is no. By theorem, any tree with 10 vertices has 9 edges, not 12, so it's not a tree. Another example, a graph with n vertices and n minus 1 edges, that is not a tree, is basically those graphs that are not connected. So by theorem, such a graph cannot be connected. One example of such an unconnected graph is shown in this, because it has 1 2 3 4 5 vertices and 1 2 3 4 edges. So it's not necessary always that a graph with n vertices and n minus 1 edges is always a tree. So you have to think, or you have to care about the other things in the definition and in theorem to conclude that whether this graph is a tree or not. It's not necessary that if a graph has 5 vertices and 4 edges, it's a tree. One such example is this. This whole graph has 5 vertices and 4 edges, so it's not a tree because it's not connected, it has a circuit. So you have to check all these things to decide whether a given graph is a tree or not. So for today it's I think it's enough. We stop here. We summarize the thing what we have studied today, and in the next lecture we shall continue this topic trees, and we shall discuss some other topics related to trees also. So in today's lecture we have discussed the relationship between matrices and graphs, and how to construct adjacency matrices corresponding to directed and undirected graphs, and how to obtain adjacency matrices from graphs. We have also discussed how to calculate adjacency matrix for the graph which has connected components. We have started today the trees. We have discussed basic definitions of trees and some of the results related to the trees. So we stop it here. In the next lecture we shall first discuss rooted tree and then further some other topics of trees. So for today it's enough. Until the next lecture, Allah Hafiz.